Saxon Advanced Mathematics, lesson 43. I'm so excited. This is one of my favorite lessons. I mean, I have a lot of favorite lessons, but this is a good one. This is one that we're going to be referring back to and talking about for a long time. I'm going to blow your mind, I hope, in a good way, with a fun new way of looking at some of the ideas we've been working with. Okay, I'm going to start by talking about some of the most useful functions that we have talked about up until now. There is, and we look at all of them on a Cartesian coordinate system. I'm gonna focus on the top half, but you can put them anywhere on the grid, right? One of our most tried and trues is the good old linear function. It makes the shape of a line, and it has, here's just an example of a linear function. It's y equals mx plus b format. You'll have an x and a y, but no squares. It is a true function in that there's that one-to-one mapping, right? And you can use the vertical line test, and you can use the horizontal, and it will pass, and we've studied it, and it's useful, and it lives in business, and it lives in nature, and it lives in engineering and chemistry and all kinds of interesting places. So yeah, there's a lot to love about a good old linear function. I'm going to draw a total of 3, so I'm just going to put in all 3 up here. Then there's something like this. We call that shape a parabola, but we call the function a quadratic function. Now, an example of the kind of equation that might, I did this wrong. No, this is right. We still have an x and a y, but the x is always squared. That changes it slightly. It's still a function, but it doesn't have one-to-one mapping, which is another way of saying we'll always get 2 values for x, right? Because of the fact that we're squaring, that makes negative numbers and their positive partners the same, right? Once you square a negative number, it's the same as squaring the positive version. So that's why we don't pass this test, right? We don't have the one-to-one mapping, but it is a true function. All right, so that's another kind. Again, these are super common in natural phenomena and in engineering type worlds, so they're very valuable. The third type we have been working with, I think it was our last lesson, wasn't it? Exponential functions. These, again, very useful in natural phenomenon. Mapping COVID has been a real thing. And these, and this is just an example of what an exponential function might look like. The variable is in the exponent. That's what makes it an exponential. And remember, they have this very distinctive kind of graph. Depending on whether the base is bigger than 1 or less than 1, right? This one is larger than 1, so it amps up on this side, this crossing point, unless we have a more complicated equation or function. This always crosses at 0, 1. This is an asymptote that we can just kind of sketch in, and then we can calculate that, but I'm not doing that today. I'm just giving you the general idea of the shape. These are all functions. Again, this passes this test, and it passes that test. In college level classes, instructors often spend a lot of time speaking about functions. They use that word as if it's something new and different, but it's not. We've been working on these things all along. We just didn't call them functions all the time. Teachers at college love to use the word functions. This is how I compare it. You already know how to read Shakespeare and write beautiful analytical essays on it, but you write them in printing, regular printing, right? You write it out like I do, right? This is printing. When you go to college, your teachers are going to do the same thing, but they're going to use cursive to write about them. They're just using a different presentation style. All of the calculations, you already know how to do all of that. You know how to manipulate all the numbers. You know how to graph this stuff. You have a huge amount of knowledge about all three of these types of functions. We just haven't been calling them functions for very long. So don't let function language freak you out. Just look at the numbers and what they're doing and you'll say, oh yeah, that's right. Okay, now today we're going to introduce a new kind of function, and we're going to be spending a lot of time talking about this. I'm drawing the same Cartesian coordinate system, but I'm elongating this x-axis, right? Because I'm going to put more variety on here. Now, this is going to be called a periodic function. And the reason why, excuse me, will become apparent in just a minute. A periodic function, this is one example of a periodic function. Whoa, right? It's like a wave. If it's written perfectly, pretend it's perfect. It's like a wave. It goes up and down in a very predictable and visually pleasing, I might say, pattern. It makes a wave, we might call. This is the graph, ready? It's the graph of the sine function. What in the world am I talking about? Okay, let me explain down here. We've been talking about sine and cosine. This is all true for cosine too, but I'm just going to talk about sine. We've been talking about sine usually this way, and we measure our angles, right? Like we might be talking about a 45-degree angle, so we draw a 45-degree triangle, and then we can find the sine of various numbers, right? We also know how to do negative angles, right? Well, this wouldn't be negative necessarily. This would be a 90 plus a 45. This would be a 135-degree angle, right? But we can also go backwards, right? We could say this is negative 135, and we could draw an angle like this. And then we could draw another one here. And these would all just be the angles of 45 degrees, right? We can draw in our 30, 60, 90s. We can draw in the quadrantal angles. We could use our calculators and find angles for, or sine and cosine for all the weird angles that aren't listed here. But we're used to arranging all our information about sine in a circle. But we also know that you can go around the circle more than one times, right? Like if we know that if you get if you're trying to find the sine of say 400 degrees, oh, that's more than one spin. That's more than 360. So we subtract and we go, oh, a 400-degree angle is the same as a 40-degree angle, right? So we can fill in weird angles, or we can do extra spins, right? Now, we have to figure out a way to take our brains from thinking of sine as being something that's organized around a circle to being something that's organized in a wave. And I've got some visual aids here to help with that. This is a circle. Pretend it is a circle like we use if we are measuring angles on a coordinate system, all right? We're gonna do this extra lesson on this circle. We call it the unit circle. And that's gonna help tie these two ideas together even more. I'm going to drop that lesson this week sometime, and so I'll tell you exactly when I want you to watch it, but within the next few days, you're gonna watch this additional video that I'm gonna show you that explains more about how this circle all comes together. It is a lesson that is not in the book. I developed it myself, but there's no homework to it. So it's just information into your brain. Okay, but let's pretend this is our circle, right? Here's 0 degrees, 90, 180, 270, 360, and we can measure different triangles on here and calculate their sines. What if we took that circle and we opened it here at 0 degrees And what if we twisted it? Do you see how the shape that I'm making here looks kind of like this periodic function that I've drawn for you? That's exactly what we're doing. We're taking our idea of how sine functions work, we've organized them in a circle, and now we're taking that circle and we're blowing it up to become a wave. What? And because we know that we can repeat, we know that we can handle sine calculations for angles larger than 360, right? We aren't just limited to one spin. The circle doesn't have such an abrupt beginning and ending. It looks more like this. See how this is a circle after circle? They get smaller, but pretend that they don't. Do you see how when we stretch out all of these circles, our circle becomes a wave function? What the actual heck? It's crazy, right? So that's what we're going to be doing, is learning how to take information that we've kind of organized in our brains in a circle and turning it into a wave. Sine and cosine are the two we're going to talk about. They work almost exactly the same. If you understand one, it's pretty easy to get to the point that you understand the other. Tangent, my friends, is a freak child. We're not going to deal with tangent until much later in the year, and he's really weird and he's not very useful. Sine and cosine are super useful for measuring things like vibrations or movement, like a pendulum swing, bouncing of a ball. These functions, like these functions that I already talked about, these are very, very useful in real life. And so periodic functions are an important part of mathematics because they tie into science. These kind of functions are also called sinusoids with a U, because they are, the soid part means similar to, this means obviously sine. So anytime we call this, see this wavy snake shape, some people will refer to that as a sinusoid. It's like a sine curve. Periodic function is what I like to call these, or I call them a sine curve or a cosine curve. This is a picture of an actual sine curve, and I will tell you how I know that later. I will tell you how a cosine curve is slightly different. And then we'll go on from there. I'm going to start the drawing on the next page, all right? So these are functions that we already know. Here is a new function, and we're just going to fall in love with this one. An example of this, we could write this as y equals the sine of theta. We can use x's, but it's very common when we're dealing with trig function, periodic functions. We often use theta, and we'll write theta like that, and y like that. That's really common. It's just slightly different labeling. You know, back in the day, we'd always just do it like this, wouldn't we? When we do sinusoid curves, we often do this little notation where we do the arrow to show the direction, and y is always y, but we often use theta, that loopy O, as a different value instead of x, but it works exactly like x. Now I want to show you the full equation of a sine function that we will eventually be getting to. We're not going to jump in. This is more complicated. Okay, this is a full-blown equation of a sine curve. This is like a little rookie version down here. We're not going to tackle all this at once. We're going to slowly build up over a series of lessons to understand all the different parts in this formula. And I want to point out that cosine has all the same parts and pieces. They're very similar. And I want to point out that there's an A and a B and a C and a D in all 4 of them. We will slowly figure out what each letter represents and how to manipulate it, all right? So this is in the future, but I just want you to see where we're going. Now let's go back, and I'm gonna draw another picture much like the one that I drew on the other page, but we're gonna deal with this one in a little more detail. All right, normally along this X or theta axis, you can use either one. We just follow John's lead. If you get the chance to describe this, you can call it X or theta, your choice. Y is always up here, just like always. No news there. And instead of having just a regular number line of 1, 2, 3, 4, 5, 6, we measure this in degrees. Okay, so the x-axis is measured in degrees. When we're dealing with a simple sine function, not a fancy wild one like this, but just a very straightforward one, that's what we're going to do here. It's y equals the sine of theta, we'll call it. We measure it in 90-degree increments. So I'm going to mark off 5 of them. This will be 90 degrees, 180, 270, 360, and then one more would be what? 450, right? Okay, so these are going up by 90 degrees. Notice that if we're thinking about our old friend, the circle, those are the quadrants, aren't they? Right? We start at, and this is 0 degrees. We start at 0, and then the top is 90, 180, 270, 360, and then we start going around again. So that's the same, okay? And then we can go backwards too, which will really blow your mind. We don't usually go backwards on our big circle, right? But we do have negative values sometimes. So that's not completely weird, right? I'm trying to help you see the link between our original circle and this. Now, if you look at our quadrantal functions, they will help you very much because at 0 degrees, sine is equal to 0. And I'm just gonna see if I can quickly put my hands on those quadrantal, that quadrantal angle chart, you know what I'm talking about? As if I have it in front of us. That will be good. Look out the window for a minute while I flip. Ponder what you did in your life to bring you to this place where you're being tortured by this woman on a video. Oh, I think we're almost there. 29? Found it. Okay, so what I'm doing is I am plotting. I'm going to cover up the other lines. I'm just working with the sine values at these 4 degrees. At 0 degrees, sine has a value of 0. There's my dot. At 90 degrees, sine has a value of 1. So let's put in a 1 right there. Okay, it maxes out. Sine never gets bigger than 1. Then at 180 degrees, it's back to 0. And then at 270, it goes to -1. So here I'll put -1, and I'll put this dot, 270, it's at -1. Now we're back at 360, but 360 is equal to 0, right? It's just an extra spin. So I can go back to this, and then 450 is gonna be the same as 90, so I can go up here. Now let's go backwards. -90 is going to be the same as +270, right? If you think of it on our circle, right? Here's our circle. This is 0. If I go down 90, that's the same as 90, 180, 270. So the value I plot here at 270 is -1. And then at 180, that would be the same as +180. I'm back at 0. Okay, So when we connect these to make a smoothly flowing sinusoid, what we have is a beautiful and perfect sine function. Now I have to go back. This is 43. Beautiful. All right. The distance from the beginning of the curve to the ending of the curve, which is easiest to see right here, from 0 degrees to 360, we know that's a full circle because literally it's a full circle, right? 360. That is called the period. It is the number of degrees that it takes to do the full range of up to down. Now we could measure that from the low point to the low point, or we could measure it from the high point to the high point. It doesn't matter as long as we're taking it from identical points and we're measuring the full cycle. Sine, we get in our heads after a while that sine starts at 0 and goes up. So that's a logical place to start it, right? It goes up and then it goes down and then it comes back. Now we're back at the starting place. So that's how we measure it. And this is 360 degrees. Later, we'll learn how to adjust that, okay? But right now, we'll look at periods that are 360 degrees. This number is called the high point and the low point. That's not very scientific. But the distance from the high point to the center line is called the amplitude. All right? We can measure it in either place. We can see that in this one, the center line is at 0, the high point is at 1. That means our amplitude equals 1. Right? And we can measure it in two places. The amplitude is not the full distance. It's the distance from the center to either one of the points. And all of our sinusoids will be balanced. We would never have one that doesn't run right down the middle. And this middle is called, I'm going to write it here. It's called the center line. And because we do have this y-axis, we could, if we wanted, we could shift it up. Like right now it's at 0, right? It's halfway between 1 and -1. So we know the center line equals 0 in this problem. But if we wanted, we could lift this whole sinusoid up and set it at y equals 15 if we wanted, right? I mean, heaven help us, but we could. So that is, I'm just trying to think if there's anything else I want to show you now. I want to show you one other thing with a different color. We can also get fancy and say, what if we wanted the negative sine curve? Well, we don't even have to calculate it. We just know that it would be kind of like the opposite. And we could sketch this in really easily. And it would go like this. Okay, so that would be the negative sine curve. This is, again, a periodic function. It's a sine curve. It's a sinusoid. And it is a function. This is a function of sine. Okay, whew, that was crazy, wasn't it? Now we're going to do the same thing with the cosine curve. So let me use some different colors so that it'll be different in your head. We start with the same basic number line situation. And I can put arrows on the ends of these. And I can put x or theta. And I can put in a y curve. A lot of times when we draw these sinusoids, we kind of pull the y-axis over a bit so that we can get in a full period of values and then repeat a little bit and then repeat a little bit this way. That's why I don't put this right in the middle. I kind of want to make sure I get plenty of space here to set up the full range of my values. Okay, we'll do the same thing here. We're going to set our center line equal to 0. It's always kind of in the way. It's a little annoying. And then we're going to go up a ways and say that's 1. And we're going to go down the same amount and say that's a -1. So our center line is 0. And our amplitude equals 1. Remember, amplitude is the distance from the center line to the high point or the center line to the low point. It's not the distance in between them. Okay, we got that. That looks good. Now, we're going to put in our degrees just the same. (90, 180), and this is also 0 degrees, right? It's 0 on both axes. It won't always be, but for now, it will be. And this is 450, and then we go -90 and -180. Now, let me just point out to you again, with cosine, at 0 degrees, cosine is 0. Got that from the quadrantal values. Oh no, I have to find the quadrantals again. I know where they are though. They're lesson 29. Here they are. Now, I'm going to show you, and then I'll get the books out of the way because this is cumbersome. For cosine, notice that our quadrantal values are different. Those are the angles. And here are the values. So I'm going to go ahead and I'm going to graph at 0 degrees. I'll graph it at 1, and so on. I'll put all these points in, all right? So I have to move that out of the way so you can see everything. At cosine at 0 degrees is 1. Cosine at 90 degrees is 0. Cosine at 180 is -1. Cosine at 270 is back to 0. And then at 360, that's one full period, right? At 360, it will be back up to the top again. And then it'll fall to the midpoint, okay? -90 is the same as +270, if you think of the circle. So it's going to be at 0. -80 is the same as +180, so it's at a low point. So now I will connect those quadrantal values and look at the shape of the cosine curve. Pretend it's perfect. I love drawing these. They're super fun. And then I'm just going to extend it because it would go down, right? Now, my pictures aren't exactly the same scale, but what I want you to notice is that the cosine curve looks a whole lot like the sine curve. It's got a period from high point to high point is 360 degrees. We measure it on the same scale. We have the same amplitude. We have the same center line. Here's what's different. Here's the only thing that's different. The cosine curve at 0 degrees is 1, and then it falls. The sine curve at 0 degrees is 0, and it climbs. That's all you need to know to remember the difference between these two. Sine starts at 0 and climbs. Cosine starts at +1 and falls. That's it. That's the difference. If we want to do, like here we showed a negative cosine. If we want to do y, oh, that's too pale. If we want to look at a negative cosine curve, we find it the very same way. We just plot the opposite points at the extremes and then we draw the opposite, okay? So negative sine or cosine is pretty easy to find. You don't even have to draw in the other one. You'll get used to this and you'll be faster at it. But you don't even have to draw in the regular one. You can just imagine. Now, where would the regular one go? Okay, if it's cosine, then at 0 degrees, I'm gonna be at +1 because that's the high point. So if I want the negative cosine curve, I go to the low point, right? It falls into place fairly easily once you play around with these a little bit. All right, let's see if I've taught you everything you need to know for today's problems. I think I have. Okay, so John is now going to ask us a few questions. Only 2. Example 43.1. Write the equation for this sinusoid. And I'm just going to put the book in place so you can see it here. Okay, we're looking here. Ignore these Post-its. Write the equation for this sinusoid. Okay, so look at it. We see it. Yeah, that looks good. We see that it starts at 0 and it climbs. So that gives us a big flat clue right away. Is it sine or cosine? Well, we know it's sine, right? Now let's check and see how its period looks. It starts and climbs there. So we'll look for the next place where it starts and climbs right there. That's at 360 degrees. Okay, so the period is 360 degrees. That's good. We're not really messing with that yet though, so that doesn't help us too much. What about the center line? That's 0, and the amplitude is 6, right? Because it's 6 up or 6 down. So here's how we write that. We know we have a sine curve. And we know that the amplitude, which I abbreviate thusly, equals 6. So we write it as y equals 6 times the sine. And do we want to use theta or x? Well, let's look and see what John did. There's an itty bitty little theta right there. So we'll use theta to match him. Y equals 6 times the sine of theta. So we calculated this number. Amplitude we found by looking at it. So this number is the amplitude. And if you look at the wacky, complicated equations I gave you, that is this number. This is the amplitude. So we'll tackle A, C, and D on another day, but today we're not even doing A, we're just doing B. That's where you write the amplitude, the distance from the center line to the extreme high or low point. Okay, so this is our final answer, and I just want to write this is B, the amplitude. All right, and then we'll just have one more, I think. Yeah, this is the last one. All right. So this one, the first thing we do is we try to figure out what kind of a curve it is. Well, let's see. It starts at the bottom and it goes up. So at first we think, well, doesn't that look sort of like a cosine, or a sine curve rather, because the sine curve starts in the middle and climbs. But this one's not in the middle, this one's at the bottom. So what's more likely is that this is the opposite of a cosine curve. It's a negative cosine curve, right? Because cosine would start at the top and go down. This one starts at the bottom and goes up. So this we're going to call a negative cosine curve, all right? Don't let that fool you that, wait, but this looks sort of like a sine. It's at the extreme instead of the center. So forget about sine when you see something like that. For now anyway. Later we're going to get trickier. But when I see it at the extreme low, I think, oh, it's related to the one that would normally be at the extreme high. Now let's look at this center line. It's 0. But what about our amplitude? 3 and -3. Okay, so our amplitude is 3. It's the distance from the center to the extreme point. So we would write this as, oh, and let's see, is it x or y, or x or theta? There it is, it's itty bitty, it's an x. So our answer is y equals negative, and then we'll put in the amplitude, and then we'll put in the type of function. This is because it's upside down, right? And this 3 is the amplitude. Make sure I got it right. Yes, oh, I forgot to write the x. Okay, so now what we can do is we can look at a picture of a sine or negative sine, cosine or negative cosine curve, and we can read which kind of curve it is, and we can calculate the amplitude. And we can put all that information into the right form. We know how to tell if it's x or theta. Just look. And we're on our way. That's all I'm going to say now. If this is freaking you out, please let me know, because sinusoids are really fun and cool. We just have to make that leap from thinking of our sinusy friends, our sine and cosine friends. We think of them in circles, and now we want to think of them in curves. But if you can imagine how that circle turns into a curve, it's going to be a lot easier to figure this out. 43 is done. Thank you. Goodbye.